Hey everyone, welcome back. In today's video, we're going to introduce a new topic. That topic is constraints. So, what is a constraint? Well, when you have a mechanism, you have bodies connected to different bodies, they're going to affect each other's motion. For example, we talked in the last video about a mechanism called a 4-bar linkage. So here is my stick drawing of the 4-bar linkage. And when we first started, we talked about how if you moved body A, and I'll write in some of the names, this is crank A, and here we have the coupler, which is B, and then we have an output crank, C. And if on crank A, if you move crank A, then this first joint is going to follow the path of a circle, which means as you rotate, the coupler is going to undergo some complex motion. It's going to translate and rotate as it follows this first joint, and that's going to result in crank C moving as well. So we can kind of see that intuitively, right? If you imagine this thing moving, but what it means is each of these bodies has some variable or coordinate associated with its motion. When we attach frames to these bodies, we know that those frames are going to be moving. So A frame, B frame, C frame. And the coordinates associated with those would be angles theta. So we could have theta 1 and theta 2 and theta 3. So this would be A frame, B frame, C frame. Now, if you grab crank A and you move it and you change theta number 1, you're also going to change theta number 2, and you're also going to change theta number 3. That means that theta 2 and theta 3 then become functions of what is happening with theta number 1. These other coordinates, they are no longer independent of each other. You can imagine if I erased this pin joint, and instead of having a pin joint there, instead of we turned it into maybe a robotic arm, right? That arm's going to come down, it's going to pick up my eraser. In this case, these three angles, theta 1, theta 2, theta 3, are in fact independent of each other. You could hold the first joint and the second joint fixed. You could activate the motor at the third joint, and that would lift that third joint. So in this case, each of these become independent. This arrangement, this is called an open loop mechanism. That's what we see here with this robotic arm. If we go back and we turn it into the 4-bar linkage again, I put a pin joint on here, this is no longer an open loop mechanism. Now this becomes a closed loop mechanism. So by closing this loop, then these joints now, right? These joints become dependent upon this one. So that's kind of a high-level intuitive explanation of what a constraint is. So there is some constraint in this problem which allows you to define two of these angles in terms of the input angle. So with that said, let's see if we can kind of narrow down the description of constraint. All right, so here is our textbook definition of constraints. 2 points. Number 1, constraints are scalar equations. And then number 2, they allow for I'm going to write a new word, generalized coordinate. Kind of ran out of room. Generalized coordinate. Let's say a solution to a generalized coordinate. So imagine, if you will, there is you have some equation, and this equation is scalar. It is not vector. And inside of that equation are some of the generalized coordinates. We're going to go over what all qualifies as a generalized coordinate. But that equation allows you to solve for one of the generalized coordinates. So In the previous example that we had with the 4-bar linkage, the generalized coordinates, there were 3 of them, and I'm just going to write GC. Those generalized coordinates were theta 1, theta 2, and theta 3. What else would qualify as a generalized coordinate? Well, this term generalized, right, it means there's all kinds of coordinates, but we're going to generalize them. We're going to group them all together. So in this case, the coordinates are rotation angles. We could also have translations, things like Q1 and Q2. And then depending on what application you're doing, you could have other things like the number of bodies could be a generalized coordinate. Perhaps you're simulating air particles inside of a box, for example. So here's a whole bunch of gas particles, and these things are all, you know, zipping around and interacting with each other. In this case, perhaps you vary the number of bodies, right? So you might have that be a coordinate. You could change things like temperature or pressure or size of the system, something like that. Now, not everything qualifies as generalized coordinates. Some notable exceptions, simply unknowns in the problems, those aren't necessarily generalized coordinates. If you have a block and you are applying a force to this block, that force is not a generalized coordinate. That force is some specified value, right? You're the engineer, you would say, okay, we need to apply 50 newtons to this block, something like that. So in that case, it's just a specified thing. So there are many types of constraints. What I'm going to do now is let me clean this up a little bit, and we're going to give a very brief introduction to several different types of constraints. We're basically just going to list them and briefly talk about them. And then in today's video, we're going to do an example of a multi-body system, kind of similar to a 4-bar linkage. It's called a CrankSlider. We're going to do the standard position orientation analysis for it, and then we're going to derive the constraint for that system. So here is a non-comprehensive list of the constraints that we're going to study in this class. In fact, we're going to add a 6th one to it when we get down to it. And the 6th one, honestly, is just kind of it's like the exception. So number 1 is the constraint that we're going to discuss in today's video. A loop, or we could even add a little comment in here. We can call this a vector loop. You will sometimes, you could see this called a distance constraint as well. And really the idea with this loop constraint, this vector loop, is if you have some system, and we'll do the example right here of that 4-bar linkage that we're familiar with. Consider that you could do a series of vectors along the lengths of this mechanism that allow you to start at a certain point, and that point is, it's usually grounded, but it doesn't have to be. But we're going to start at this point. We're going to go through the mechanism. We're going to go to another point, and in this case, it's the other grounded point. And then we're actually going to go through the ground itself. We're going to use these offsets to come back to the original position. So in so doing, we've used vectors and we have made a loop. Now remember, the number 1 rule of constraints is that it's a scalar equation, and this is literally vector, right? So of course we have to do things to take our original vectors and we have to turn them into scalars. So this is the example, or this is the constraint that we're going to do in this video. I'm not going to do a 4-bar linkage. We're going to do something different called a CrankSlider in just a moment. Next though, let's briefly talk about these other constraints. And I'm actually going to do a couple more videos, and we're going to do worked examples of each one of these. So gears, consider that if you have 2 gears that are meshed together, and there's my symbol for the gear teeth meshing, and you take the first gear and you spin it, because these 2 things are meshed together, clearly the other gear is going to turn as well. So if you had theta 1 and theta 2, and you changed theta 1, you're going to change theta 2. So theta 2 then becomes a function of theta 1. And again, that's the whole idea with the constraint, right? Is that these 2 generalized coordinates are no longer independent. So there's your gear constraints. We can say a similar thing about pulleys. If you have two discs that are connected by a pulley, and there's your theta 1, there's your theta 2, well then when I rotate this first disc, it's going to move the pulley, right? It's going to move that belt through the pulley system, and it's going to spin the second disc. So we're going to do that one as well. Pulleys and belts, these two constraints end up being almost identical, small difference between them. Ropes and cables, you might have seen problems like this before. You have some disc up here, and you've got maybe a block connected to this one, and you've got a block connected to that one, right? And of course it can get more complicated than this. But clearly, if you were to grab this first block and you were to pull it down, well, unless something happens with this rope, then the second block is going to go up. So we're gonna do some problems with ropes and pulleys, cables, ropes and cables as well. And then this last one is a lot of fun. So arc length. Recall from your math classes when we talk about arcs, we're talking about taking a circle and just cutting a section out of it. And the arc then is that portion of the circle. And then the arc length is the linear length. If you were to perhaps cut this circle and then just lay this section out, right, you would get a length. And we can use this kind of arc length analysis to look at rolling bodies. So wheels or discs or something that are sliding on the ground, as this disc spins, if we assume that it is a no slip condition, and again, we'll go into that in detail, but if we assume no slip, then as this wheel spins, it is also going to roll along the ground. So there is a rotation, and there's also a translation. So this wheel, from the initial setup, you might think it has two generalized coordinates. Well, it does have two generalized coordinates, but they are not independent of each other. So in each of these cases, we can kind of just look at the problem, and we can visually or intuitively understand that that these coordinates have some kind of connection, right? What we have to do is we have to come up with the mathematical equations that connect them. We need to be able to solve for a change in displacement given some change in angle, something like that. All right, and then what about this last one? Well, I like to include a final point just to say that there's all kinds of problems out there, and you could encounter strange geometries. So for example, it could be some kind of geometric constraint, and you are going to encounter one or two of these on your homework assignment, so just be aware. Not everything is going to fit nice and clean into these categories. So when I say geometric, what does that mean? Maybe you got to bust out some trig. Go back in time, you've studied the law of sines, law of cosines, all kinds of stuff, right? And sometimes you might have to combine different constraints or take a piece of one and add it to something else. So just for number 6, just keep it flexible, right? There's always exceptions. Okay, so what we're going to do is let's get started on the problem, and we're going to do position orientation, and then we're going to work up to this vector loop. Here's the mechanism we're going to look at. Here's our CrankSlider. This is 3 bodies. The first body is our crank. The body in the middle is the coupler. And then this last body, that is our slider. Sometimes you will also hear people say, instead of CrankSlider, you will also hear slider crank. And there is a difference between them. The mechanism itself is exactly the same. What changes is the input. In a CrankSlider, the input is the crank. That means, imagine you have a motor at this pin joint that is providing a torque that is making this crank spin. Okay. In the other case, in a slider crank, the slider is the input. So there is some motion now of this slider, and that's going to make the coupler move, and the coupler is going to make the crank move. Notable example of a slider crank is internal combustion engine. So this would be the piston in your engine. There we go. And here is your combustion chamber. We're going to pump some high pressure air into this. We're going to inject fuel into it. This slider is going to compress. It's going to drastically reduce this volume. You're going to spark it. The fuel will combust. The high pressure gas is going to be generated. The oxygen fuel gets converted into CO2 and water. You're left over with basically nitrogen, hot nitrogen, and that's going to expand rapidly. It's going to push against this thing. So this slider moves out. That makes the coupler move, and then that's going to force the crank to turn, and that is the output shaft of your engine. And then it goes through transmission, drivetrain, etc. So we're not going to worry about that much in this class. We're not going to worry about what the input is. For the mechanical engineering students in the room, you will study the difference between these because there ends up being a little bit different how you solve for the outputs, for example, when you take the kinematics and dynamics of machines class. So you'll continue to see these things as you go through your classes. So what we're going to do though is we're just going to call it the CrankSlider and be done with it. And what do we need to do? Well, let's say that this is your problem statement. What do we want? We want, I'm going to list something, a new term here, and we want the number of degrees of freedom. Now, you might have heard this phrase before, degrees of freedom. We use it in a lot of different instances. For example, in linear algebra, if you have a non-square system, perhaps you have some additional degrees of freedom, which in that case takes on the form of like a free choice in the system, something like that. So this does get used in other applications. What do I mean in this case when I say degrees of freedom in dynamics? Take the number of generalized coordinates and then subtract the number of constraints, and that is going to give you the number of degrees of freedom. I usually just shorten it to DOF. And really what degrees of freedom means is how many of those generalized coordinates are independent. So for example, we've already talked about the 4-bar linkage. We said there were 3 angles, theta 1, theta 2, theta 3. There are 3 generalized coordinates. The degree of freedom is how many of these things are independent. So just looking at the diagram on that 4-bar linkage, intuitively, we could look at this system and say, well, there's only one that's independent, because as soon as I move that first one, I make the second one move. And when the second one moves, it makes the third one move. So theta 2 and theta 3 then are dependent on theta 1. So if we have this equation then, and we know there's 3 of these generalized coordinates and there's 1 degree of freedom, only 1 of these are independent, well clearly the number of constraints has to be 2, which it is. So you're going to have to do some 4-bar linkages on your homework. We might, we are going to continue to do these as we go forward, and we'll continue to look at the constraints. But what we're going to do is we're going to do one that's slightly different, right? This is a little different than a 4-bar linkage, but if you see what we do on this mechanism, you can absolutely do the 4-bar linkage. So the goal then, when you read a problem statement that says, determine the number of degrees of freedom, maybe you can look at this thing and you can say there's 1 independent coordinate. That's not good enough. This statement right here where it says we want the degrees of freedom, that means you have to, you got to follow a certain process. Ultimately, we're looking for the constraints, but the process is really this. You have to do position and you have to do orientation, because no matter what the problem is, that's where you begin. We're going to list the generalized coordinates, and then we're going to derive, or we're going to write down, we'll just say derive. We're going to derive the constraints. So this is our approach for analyzing these problems. And in fact, as we continue to move through the semester, this is the process going through these problems. Think of this approach to dynamics as a recipe. I'm going to give you a set of steps. You follow those set of steps, and if you follow those set of steps for every problem, you can solve every problem. And it doesn't matter how complicated the dynamics problem gets. This is your approach. So we're going to do position. We're going to do orientation. The number of generalized coordinates, these usually come from position and orientation. Now, sometimes when you start working on your constraints or working on future, other parts of the problem, you might realize that you need additional generalized coordinates. That's fine, that happens. So you just go back and you add it to the list. All right, let's clean this up, and let's do that for this CrankSlider. So we've done a couple videos now where we're talking about position orientation. The first homework is on that topic. I don't expect that you're experts at this point, but we don't have to go into quite as much detail in the previous videos. Where do we begin? The process is the same every time. We need to put an inertial frame on this problem. So the end frame, there it is, x in, y in. We need to identify some easily seen, intuitively known, non-moving point, and make that our inertial reference point. So what's a good place to put on this one? Well, pin joints are always a good place. These grounded pin joints, that's not bad. You could, if you want, you could put it at the back of this this combustion chamber, right at the back of that slider casing. Places you can't put it. You can't put it here because that's a joint and that thing's going to move. You can't put it right here on the block because the block's going to move. So let's put it at this point right here. Now we need to label some other points on here. As we've talked about several times, positions, right? We need to be tracking some kind of position on every single body. This is a good example of maybe we don't have to do, since there's 3 bodies, maybe we don't have to do 3 more points. For example, if we put point A on this joint and I put point B at that joint, those 2 points actually do a pretty good job of tracking those 3 bodies. Point A is on body A, and point B is now the tip of body B. And if we want to, we could put another point, we could do the center of mass, and we could call the block body C. But point B is also on block C, which means if I know where point B is, and I know the geometry of the block, I can very easily tell you where point C is. So in this example, this is a good case of maybe it's not needed. So you could save a little bit of time by not tracking it. Now, of course, once we get later in the semester and we talk about momentum, we have to keep track of every single center of mass anyway. So just be aware, you can't always take those shortcuts. Okay, so what we're gonna do is we're just gonna focus on points A and B. We're gonna save a little bit of time in this specific problem. And let's do position vectors first. So P in A and P into B. So how should we keep track of these points? We need the position vector from N to A. This looks familiar. If we cover up the right side of this problem, that is simply a pendulum, right? It's just going to spin in a circle. We know that we got to put a frame on this, so I'm going to put the A frame like that, XA and YA, and then we can come over to the position vector and we can define this as, let's say, L1 X hat A. All right, so what do we want to do for the next one? We want to keep track of the motion of point B, the position of point B. Now, you might be thinking we can go into A to B. That's good. We're going to need to do that. I'm going to go ahead and write that down. Plus P A to B. And now we could simply solve for P A to B. But pause. Consider that there is another thing we could do. Let's say there's some small offset between these, right? general case, so we can build in some kind of vertical offset. We're going to need an L2 here, and I'm going to call this vertical offset, I'm going to call that offset L3. It is constant, right? Some vertical displacement between point B and point N. But this slider goes back and forth, and that's a variable distance. So we could put in a translation variable as well, and that is another way that we could get from point N to point B. And both of these ways are valid. And in fact, in this problem, we're going to use both. So let's do this first one. We need to get from point A to point B. We've already written down the distance, it's L2, and we need a direction for it. Okay, well, remember, every body gets its own frame, and you get to pick how the frame is oriented. So let's say along the length of it is XB, and perpendicular to it is YB. That makes this position vector L2XB. All right, what about this other way? If we wanted to go directly from point N to point B, well, we said there's the vertical component, so hey, okay, let's go ahead and bring that in. It's L3. In what direction? We can use the inertial frame for this. I can say it's L3 in the y hat in. That moves us up. And then we have this, this translation Q in the X in. Now, both of these are valid ways to get from point N to point B. So this is going to take care of the position. In fact, I'm just gonna leave this stuff up here. So in your notes, just have both of these written down, and we'll come back and we'll talk about them. Now, I am leaving one thing off of the diagram. It may seem trivial, but it is important. We have to put a frame on the block as well, and I'm just gonna put C with a hat on it. I think y'all can see that this is XC in the horizontal, YC in the vertical, and it's aligned actually with the in frame. So is it necessary? Yeah, it's necessary to put it on there. Once you get out of my classroom, maybe you don't think it's necessary, but for now, while we're learning, I need you to put a frame on every single body. Okay, so that takes care of the position. Let's knock out the orientation. All right, I'm gonna erase that too, just to give us a little bit more room. So what do we do with orientation? Well, how many frames are in the problem? There's the inertial frame, which I just erased. There's the 3 body attached frames. I need you to define the rotation for every single body attached frame. So what are we gonna do? We're gonna do our diagrams. We're always going to draw it in quadrant 1. It doesn't matter. For example, XB is currently in quadrant 4, right? It's pointing down and right, but the trig expressions work. If you just derive it from this initial quadrant 1 diagram with the sines and cosines, even when it's in quadrant 4, it's still true. X in, Y in, X A, Y A. And here's our first rotation, theta 1. Everything that we've been doing, all these trig expressions, we're just going to do them again. XA, YA, ZA. ZA is the easy one. ZA is equal to ZN, right? We're doing this rotation around a shared Z axis. And then all of these same definitions, cosine theta 1, XN, sine theta 1, YN, negative sine theta 1, XN, and cosine theta 1, YN. What is this? This is the rotation from N to A. Once you have a position vector to some point on this first body, so P into A, and once we have the rotation, then we can make the location description of A, and we can just drop those things in there. There we go. All right. unless you're doing some other kind of rotation, rotating about some other axis, this does not change. So you're going to get tired of writing it. I need you to do it. Okay, this is how you communicate to me in the grader that you know what you're doing. So what are we going to do for the other bodies then? Well, the B frame is also rotating, right? And we talked about this in a previous video, the difference between relative and absolute angles. If you don't know what I'm talking about, go back and watch the video on 4-bar linkage. But it's really just about how do you measure the angles and what do you measure them with respect to. So for the B frame, let's make it easy on ourselves and let's just do absolute angles. So XB and YB. I do, of course, encourage you to try out relative angles and see what you think. It's how you have to work three-dimensional problems. And then we would just go through and, you know, write all this down again and just make the little changes. This is now XB, YB, ZB, and these are all theta 2s. And then this rotation is the rotation from N to D. Okay. So what do we do about the C frame then? Well, just visually we can see that block's not going to rotate, which means the C frame doesn't move, right? Okay. Do you still have to do a diagram? Yeah. No, I need you to still do a diagram because again, that's how you show me in the grader you know what you're doing. So what kind of diagram do you need to do? For a frame that doesn't rotate, just do this. And say XN, and you can just write next to it XC, YN, YC. There's a lot of ways to show this, but I mean that's basically it. X, let's see, C frame, yeah. So XC is equal to XN, YC is equal to YN, and ZC is ZN. I have sometimes seen students do the same diagram and they'll put the same trig expressions here, and maybe they'll say something like cosine of some fixed angle, right? We could say like cosine x at n plus dot dot dot, and then they come back and they'll write a comment that this angle is fixed. That's okay. You could say that angle is equal to 0 or something. That's okay too. Sometimes this approach right here is actually very useful because what if you have a block that is sliding up a hill, and we've seen this in some of the homework assignments. We've had blocks on slopes. Sometimes students will want to, in this kind of problem, they'll want to turn the inertial frame. They'll say XN and YN, something like that. And I'm going to strongly advise you, do not do that. The reasoning why you don't want to do it. The inertial frame is very much representative of the observer. You're the observer looking at this machine in operation. And to you, that's not up and down, left and right. But also beyond that, consider, what if we start talking about the weight of this block? Right? There's gravity acting on it, and gravity is going to act that way. Regardless of how you have chosen to rotate your inertial frame, that's how gravity acts. So even if you rotated the inertial frame, we still have to have some other frame talking about how gravity is acting on this. So good practices, just leave the inertial frame as it is, up, down, left, and right. And then we could actually define, well, we put a frame on this block, right? And that block, the frame on the block, is rotated through a fixed angle. So you can do this for this one, and you would just say, instead of calling it, some fixed angle, you would just say, hey, it's equal to 0, all right? Or you could do this. This is perfectly fine as well. Up to you. All right. So you do this. And what is this equal to? This is the rotation from N to C. And that's it. That's position and orientation for the CrankSlider. Now, the problem statement was we want to know how many degrees of freedom there are. So what happens next? The next thing I'm going to ask you to do is I'm going to ask you to list the generalized coordinates. So what were the generalized coordinates? They tend to come out of position and orientation. If you do the position orientation, you usually have a list of all of the generalized coordinates to begin with. Now again, sometimes you go back and you have to add some, but just look at the diagram and ask yourself, on this diagram, what is changing? First of all, there's a translation variable. That's an easy one. That's changing. But how do we characterize, or how do you think about body A and body B rotating and changing? What variable is associated with the motion of body A? Well, it spins, right? And we're not assigning Q1 and Q2 or anything. We're not using the inertial reference frame. We're using this body attached frame. So recognize that the A frame is a function of theta 1, and the B frame is a function of theta 2. So there are two more generalized coordinates. So when you go to make this list, we would list Q, theta 1, and theta 2. Now, I do want to make a point about this Q. I very specifically went out of my way to go position vector into B, first through the mechanism, and then again directly, right? So what if you hadn't thought about that one? What if you just did that? And on your generalized coordinates, you only have 2. Okay, that is not incorrect, all right? That is not incorrect. But what we're going to find when we do our vector loop, if you hadn't already cooked it up, we're going to have to, all right? So we've got these generalized coordinates. List them out, tell me how many there are. So right now I've only got 2 written down, the Q makes 3, right? So what we need to do next, once you list out those generalized coordinates, the next thing I need you to do is derive the constraint equations. So what is the constraint equation on this CrankSlider? So this problem now, we're doing a CrankSlider. This is now going to be an example of a vector loop. Vector loop is a type of constraint. So what we want to do in a vector loop is we want to start at a certain point, we want to move through the mechanism, and then we're going to come back to the point. Now, what we're going to do in this problem is we're going to start at a grounded point, we're going to go to another grounded point, and then we're going to use the ground to come back to the original point. There are some exceptions to that, where you perhaps don't start at a ground at all. And I can very quickly give you an example of that later. For now, that's what we're going to do. We're going to pick a grounded point in, we're going to go through the mechanism, we're going to come back to in. So let's start very slowly at the top. I want to do a position vector from point in to point in. Now, that seems almost silly. What is the difference between these two ends? Nothing. It's the same end. What's the distance between these point ends? Nothing. The distance is 0, but we're going to do this. So how do we approach this? Let's go from point in to point A, and let's go from point A down to point B, and then let's go from point B back to point N. Some other things we could have done. Remember at the beginning of the problem, we put the center of mass on the block. We could, if we wanted to, change this a bit. I could say, well, what if we went from B to C, and then we went from C to N? It ends up being the same thing. Consider that to go from point B to point C, it's a fixed distance in the x hat n direction. And then when you come back from C to N, you're just going to go right back through that same offset. So this ends up being nothing. It ends up canceling. So feel free to do it if you want to. Feel free to work it both ways and prove to yourself that it does end up being the same thing. Now, next thing we want to do, we want to fill in these blanks. Some of these we already did. This P into A and this PA to B, we actually did that as a part of our position. That's P into B. right? What about this last one? Here's a fun thing. If I write P, B, N, that's actually just negative P and B. If you reverse the order, right, instead of going from A to B, if you go B to A, you literally take the same position vector and you just put a negative on it. Now, I know that if I put these things together now, we're writing P and B minus P and B. But recall, if you go back and look at the positions, we defined, this is like saying P and B, comma, number 1, and this would be P and B, comma, number 2, because we did it twice, right? So let's put the details of it into this expression. All right, so I'm going to drop this P into N. I am going to carry down the 0. The 0 is actually very important. So P into A, that was L1 x hat A. PA to B is L2 x hat B. Now PB to N, I'm going to say plus. Actually, let's do it this way. Up here, I'm going to replace this one with minus P in B. All right? So I'm going to put a minus on here, and then we're going to open up parentheses, and we're going to drop into this that other way of getting from N to B directly. So what do? We did L3 y in, and we did Q x in. So this was going from N to B, and now I just have a negative on it so that we're going back. All right. Let's see if this makes sense, right? Pause here for a moment. You go L1 in the x hat A direction, that gets you into A. You go LB in the XB direction, that gets you down to B. You go down, right, because it's negative now, distribute the negative. You go down the distance L3 in the y hat N direction. And then some people get a little tripped up with this. Remember, we've talked about how my personal habit is to just treat these things like they're positives. Okay. Here was Q, and Q gets us from N to B. Q gets us from N to B regardless of the instantaneous value. It doesn't matter if at the present moment the value of Q is positive or negative. We are defining Q from N to B, which means if you go in the other direction, right, we put a negative on it. That means now we're going from B back to N. So this expression gets us through the mechanism and gets us right back to point N. So what was the point? What was the point of doing that? Let me take this, and I'm gonna move it up here so that we can keep working. All right, so I'm just gonna copy 0 equals L1 XA, L2 XB, I'm gonna say minus Q XN, and then there's the minus L3 YN. All right. So there's our vector loop. Remember the first rule of constraints. First rule of constraints is that it's scalar. This is not scalar. This is vector. What do we need to do to make this thing be scalar? Well, if you want to get rid of your directions, you need to use dot products. So we're going to take this vector equation and we're going to do a dot product. Let's say we're gonna cook up equation number 1 now. We're going to take that position vector P into N, that's our vector loop, and we're going to dot it. What do we need to dot it with? Well, you dot it with a direction. So if I dot it, let's say with the x hat N direction. First of all, we know that P into N is equal to 0. So if you dot it with something, it's still equal to 0. Okay. So what happens next? That means that we're taking each of these in turn and we're going to dot them with x hat N. You could take this dot product and you can distribute it amongst each of these terms. So it's like taking L1 x hat A, and we're going to dot that with xn. And then we're going to do L2 x hat B, And we're going to dot that with x hat n plus dot, 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 right? However many terms are in this expression, we're going to take each one of those and we're going to do a dot product. How do we do that? Well, we did this on in the previous problem. We talked about how you can replace x hat a and x hat b and y hat c with the expressions from the rotations. So let's say L1, and I'm going to replace x hat a with cosine theta 1 xn plus sine theta 1 yn. And then we're going to take that. We're going to dot that with x hat n. Next, let's do the same for the second part. So plus L2, this is cosine theta 2 xn sine theta 2 yn. And I'm going to go ahead and bring these last two terms down as well. So it's minus q xn. I tell you what, these are both inertial frame. Let's combine them. So let's say plus, and now it's a negative q xn minus L3 yn, and then we dot that with xn. Okay. If we're going to do this, you need to know what a dot product is. And every semester, people are a little rusty on dot products. That's okay. So I'm going to erase this bit at the top and let's talk briefly about dot products. Dot products are vector operations. What does it do? People talk about it's like the projection, right? Or people say it's the cosine or something like that. Here's what it really means. You've got one vector, and I've got another vector. The best way to explain it graphically, in my opinion, is the projection. It is what portion of, let's say this is A and this is B. It's like saying what portion of B gets projected down onto A. And sometimes people will say, oh, it's the cosine of the angle between. So whatever this angle is, right, it could be the cosine of that. And that's fine. In this case, we've broken it into its projections already, right? We've said, here's the x hat n portion, here's the y hat n portion. So using that, now we just have to know what is x hat n dot x hat n, and what is y hat n dot x hat n. Well, x hat n and x hat n are the exact same thing. They're parallel. So what is the projection of a vector onto itself? It's 1. And then y hat n and x hat n, these are perpendicular to each other. They have no projection onto each other. So the dot product there is 0. That's why I put it into the x hat n and the y hat n's. Now, when you're doing an exam, if you know how this gets resolved, you do not have to show me each individual, every single little step. I absolutely want you to show your work, right? You have to justify your answer, but don't think that you have to do everything. You show me, you show the grader enough that we know that you know what you're doing, okay, as always. So, what's going to happen to this, this expression down here then? Knowing those dot product rules, I'm going to write, here's our equation number 1 again. First thing I'm going to do is I'm going to bring the 0 up. The equation is still equal to 0. What happens in this first term? Well, there's a distance out front, L1, that does not change. We have an x hat n component, and it's xn being dotted with xn. We said that that's equal to 1, right? You lose the directions, and what you were left is just the scalar component. L1 cosine theta 1. And then what happens to the y hat n? This is now equal to 0. We go on to the next part. So plus L2. It's I left it off. There we go. Okay. xn dot xn is going to equal 1, yn dot xn is going to equal 0. We're going to be left with just the scalar portion, so cosine theta 2. And then what happens down here? These are already in inertial frame. Yn dot xn is going to equal 0, and we're going to be left with minus q. So there is equation number 1. Now, perhaps going back to geometry, some of you, I'm sure, could have just looked at this thing and could have figured that out, right? That's good. Intuition is good. You could probably figure out that L1 multiplied the, and you add on that little portion. It's just like adding the horizontal portions of this piece and then this piece, and then clearly that equals this total distance. That's fine. I assure you, these can get more complicated, right? So it is useful if you're able to do this in a methodical manner, because these do get, or they can get more complicated. All right, so there's equation number 1. What about equation number 2? There's a whole nother direction here. We just dotted with x hat in. Couldn't we also dot it with y hat in? Yeah, of course. I don't even have to rewrite this whole thing. Let's just change the dot products. So we're now dotting with y hat in. Okay, what happens this time? Well, this time the x hat in is going to go to 0. X hat in dot y hat in equals 0. And your y hat in dot y hat in, this becomes 1, and you lose the direction. So these equations, again, it's equal to 0. We have L1 sine theta 1 plus, same thing's going to happen here. The xn component is going to be 0. Yn dot yn, we're going to get L2 sine theta 2. And this time, the q is going to go to 0. And we're going to be left with minus L3. Okay, what was the point of doing all that? I'm going to erase this. We're done with this part now. Take a look at these equations. Equation 1 and equation 2. They are scalar. These equations contain the generalized coordinates. And if we really wanted to, we could use these equations to solve for 2 of the generalized coordinates in terms of 1. Another way to say that, we have 3 generalized coordinates. You could think of this as 3 unknowns, right? And we know that if you have 3 unknowns and you had 3 equations, for example, you can solve for all of the unknowns explicitly. It becomes a system of equations. Same number of unknowns as equations, you get an explicit solution. Now, what happens if you have 3 unknowns and only 2 equations? That means there's not an explicit solution. That means that your system has an input, and you get to pick that input, or it gets specified or something through the motion, and then you solve for the other 2 in terms of that input. So we said that this was a CrankSlider, which means the input is theta 1, and then imagine that you can use theta 1 to then solve for theta 2 and the translation q. Here's the equations to do that. Now, these equations can be kind of nasty. These belong to a class of equations called I'm going to try not to screw this up, transcendental. Yeah, okay. That might be it. Might be how it's spelled. Transcendental equations, it's a fancy name. It really just means they transcend normal trigonometric equations, something like that, or normal algebraic equations, etc. Notice that the unknown variables are inside of these trig functions, right? Obviously the q is just kind of by itself. But if you were going to solve for this theta 2, for example, let's say you're going to use equation 2 and you're going to try to solve for theta 2. We are not going to do that in this class, all right? If you're a mechanical engineering student and you take the kinematics and dynamics of machines course, you will study how to actually solve these equations for those unknowns. It is not as simple as it looks. It's not as straightforward, and I can prove it very quickly. Let's say that we want to solve for theta 2. We're going to pick equation 2 because there is no q in it, right? But there is the input theta 1. So let's say I move these two pieces to the other side. So we've got L2 sine theta 2, and we're going to set that equal to L3 minus L1 sine theta 1, right? That makes sine theta 2 equal to L3 minus L1 sine theta 1 divided by L2. So how do we get theta 2, you might ask? Some of you are going to say, oh, well, can't you just do sine inverse theta 2? There's a problem with doing this. And it's the same problem if you had used number 1. If you had used number 1, you'd be doing inverse cosine, right? Inverse sine and inverse cosine are both 4-quadrant ambiguous. Consider that there are two angles that would give you the exact same sine measurement. These two angles, right, if I had drawn them perfectly, those would give you the exact same sine. So when you do inverse sine, which one does it give you? Does it give you quadrant 1 or quadrant 2? It's not going to give you both, right? And even if it did give you both, which one is the correct answer? Okay, so that's why we don't take these equations and just do a straightforward solution on it. The actual solution is a little more complicated, but it will give you 4-quadrant specific answers. What you'll realize later, though, when you study it, is you trade one ambiguity for another. Even though there's no longer two angles, there ends up being two different mechanisms that can actually come out of it. So it ends up being kind of a fun analysis if you enjoy painful things. So at this point, these two equations, these are your constraints. They're scalar equations and they contain the unknowns. And if we were so inclined, we could do some nice math and we could use them to solve. So what do you do next in the problem? I'm going to ask that you do one more thing, and you just you kind of tie all this stuff together, and you tell me that there are 3 generalized coordinates. You have 2 constraints, and that is going to leave 1 degree of freedom. Now, I had commented earlier, what happens if you start this analysis and you leave out the q? And realize that in order to do the vector loop, right, in order to get back from point B to point N, you would have had to create q. So somewhere along the way, you're going to need that q value. You will, a couple final closing comments, you will sometimes see these problems worked, and maybe we leave the q out completely, okay? How can we get away with that? Suppose that we only, when we did our vector loop, suppose that we only looked at the vertical displacement and we didn't look at the horizontal displacement. The vertical displacement is fixed, right? L3 is a fixed distance. So we could have approached this with only 2 generalized coordinates, and we could have written only equation number 2, in which case we would have had 2 generalized coordinates, we would have had 1 constraint, and at the end of the day, we would have still ended up with 1 degree of freedom. I think perhaps in the 1 or 2 places in the textbook, and you might see this other places, instead of calling it a loop constraint, in those cases, they will call it a distance constraint because there's a fixed distance, a fixed vertical distance between these. My personal approach, my personal style is to I just do a full vector loop and then I just write the extra equation. And honestly, once you've practiced this a lot, once you've done these dot products, you're going to be able to crank these equations out very quickly. And you are going to get a lot of practice doing it. Okay, I think that's probably good for this video. There's a handful of points in here about constraints and degrees of freedom that we're going to continue to hammer home on the next series of videos. Consider that what would the difference be if this were a 4-bar linkage? I think after having done all of this, you could probably sort this one out. But you go through the mechanism into A to B to C, and then you go back from C. You go from C back to N. And there's some, now it's 2 fixed distances. You have a fixed horizontal and a fixed vertical, right? Fixed horizontal, fixed vertical. And there's no translation variable, but now you have theta 1, theta 2, and hey, theta 3, because the C frame rotates. So still same story, right? 3 generalized coordinates. There's going to be 2 constraint equations. You do your dot products in the x and the y, and you end up with 1 degree of freedom. Okay, so I'm happy with that for this video. We're going to come back with the next round of videos. We're going to look at those other constraints. So best of luck. I will see you next time.